Right, time to get started. So this lesson 10 seems to be sort of a transition of the course into a new mode where where the lectures are pretty dense, but not only that, they're not even half the story. I mean, they have references to papers that they don't even cover, and I suppose that if you really wanted to get everything out of the course, you'd have to go in and look at those papers. And so, but I'm going to concentrate today on just getting through most of this presentation through the slides. So let's see. He starts by, okay, so this is the lecture plan he's going to cover, and most of it is well, the first part of it is final project notes and so on. But then he's basically talks about the squad data set, which was actually invented by one of the graduate students in his program. And then the model that, question answering model that they built, and this is built by one of his TAs in the program who's now gone somewhere else. And then this model called BIDAF, bidirectional attention flow. So we'll mostly talk about those things, and then he skips really fast over this last part, so we're not going to really spend that much time on it. Yeah, so let me basically going to try to cover 3, 4, and 5 today. So let's get started. So here he talks about the final project. Then he starts talking about question answering, and so the idea is that if you're interested in some topic, then and you can build a system that will find the documents that are related to that topic, but then that still gives you a lot of work to do reading those documents. So so the idea was to build some kind of a system that could ask questions about a document, ask questions about the content of a document, and return the answers. And I guess ultimately the idea is to be able to do some kind of a detailed querying of a topic to find out any kind of information that you're interested in. And I'm not sure what the state of the art is on that today, but that's what they're really trying to do. And this question answering that we're doing in this lecture is kind of like a very primitive form of that. So here they're just asking a question, and they of a passage, and then the answer is just some piece of the passage that contains the answer to the question, and that's a really rudimentary form of question answering, and it's far away from reading comprehension, which is able to reason and give detailed answers. Let me find out about. Is there a question? Okay, I'm going to have to mute some people or somebody. There, that's good. We're good. Okay, so the idea is then they're going to just try to find a limited. They're just going to try to treat a limited portion of this broad question, this broad idea of question answering. They're just going to find a passage in the topic that sort of contains the answer to the question. So it's kind of like a divide and conquer strategy. They're trying to address a complex problem by breaking it down into smaller pieces that they can address. And so this kind of they call it a reading comprehension test, whatever. It says a machine comprehends a passage of text if for any question regarding that text can be answered correctly. Okay, so there's two things. It has to answer the question. You have to, human beings have to agree that it answers the question, and they also have to agree that it doesn't contain extraneous information that you didn't ask for. So that's like the general idea of machine comprehension. So you have a passage and a question, and you're given a passage. you're given a question, and then you find the answer to the question. So here's an example, a passage, and then it's about Alyssa traveling to Miami, and the question is, why did she go? And to answer the question, you have to figure out that she went to visit some friends. To be clear, this is not what today's lesson is about. Today's lesson is about a much simpler form of question answering, where you're just going to find a passage, you're just going to find a portion of the passage that provides an answer to it. It's just limiting to the kind of questions that can be answered by a piece of text from the passage. So, and he calls that a span. So this is basically some history, and now we're going to get to this thing, Dr. QA, that in this lesson. This was produced by some people at Stanford, I guess. And they use a neural network model to bring deep learning to open domain question answering. Okay, so this drawing, this is very busy, but the idea is that there are different kinds of questions. Factoid question is just a question that has an answer like a year, or a specific thing like who won the World Series in 1981, something like that. Let's see, definition question, list question. So this is basically an overview of what this question answering system has to look like. And apparently they've done a lot of work in this area even before, even around the early 2000s, but they hadn't used neural networks, and they were still getting some kind of results. So, but this, today's lesson is about the application of neural networks to this. And so so they built this special purpose data set to test people's question answering systems. But again, it's a very restricted form of question answering. The idea is that the questions are limited to those questions which have an answer that is a span in the passage. So there's not necessarily any semantic reasoning involved. You're just looking for something that answers the question. So let's see. I got to get rid of this thing which is in my way. See, how can I do that? I don't want that. Okay, so they call this extractive question answering. I don't know how to get rid of this menu that I don't want, but anyway. So they built this Stanford question answering data set, which is called SQUAD. And actually, a graduate student, Raj Purkar, who was at Stanford at the time, I think he still might be there as a graduate student. He's just graduated or he's about to graduate. But anyway, he built this data set of 100,000 questions and he actually used Mechanical Turk to get the answers. Mechanical Turk is where you can get people online to do simple tasks for you for small amounts of money. And so he had people, he used Wikipedia, and they extracted 100,000 passages from Wikipedia, and then they had people give answers, and they gave three different answers so that you could have a choice, so that it would make the scoring a little easier. So 3 different people had to choose the answers, and so sometimes the answers wouldn't be exactly the same. So here's an example, a passage, and then here's a case where a question where all 3 gave the same answer, and here's a question where all 3 gave the same answer, but then here's a question where 2 different answers were given. So that just makes it a little bit more lenient in the scoring, because there could be possible different answers. The first version of SQUAD 1.1, all questions had answers, so that in a sense made it easier. That is, there weren't any questions you could ask. You weren't allowed to ask questions that didn't have an answer in the passage. So, and then there was two ways of scoring. One was exact match. You had to get one of the three answers, or you got a 1 if you did that, and a 0 otherwise. But then he says that the F1 score is much more. I guess he says it's much more useful as a metric, and the F1 score is just as we expect. It's the precision. It's the harmonic mean of the precision and the recall. Where remember what precision is, you always have to. Sometimes you always have to go back to the Wikipedia page, but precision is basically the detection efficiency for positive cases. So true positives over true positives plus false positives. That's the fraction. That's basically, so true positives plus false positives. Sorry, I got that wrong. Let me start with recall, because that's what I was talking about. Recall is basically the detection efficiency for positive answers. So the denominator is all the positive answers, all the answers which should have been positive. That's the true positives and the false negatives. Those are the actual positives. That's the denominator, and the true positives are the answers that answers that you ranked as positive, the positive cases that you ranked as positive. So that gives you the recall, which is sort of the detection efficiency for a positive answer. And then the precision is almost the same, but look at the denominator, is a bit different. On the denominator, it's true positives plus false positives. So that's all the times that you said something was positive, and the numerator is the times that it really was positive. So this is kind of like classifying your ability your ability in classifying positives. In other words, what fraction of all the times that you say something is positive, that's really positive. So this is kind of like a reliability score. It sort of tells how reliable you are as a classifier of positive cases. And then the harmonic mean is just, well, 1 over the harmonic mean is 1 over the precision plus 1 over the recall. That quantity divided by 2, and then if you solve for that, then you get this. It's just twice the precision times the recall divided by the precision plus the recall. So this is a well-known metric that often gets used, and it basically tries to combine both of these things. A metric that tries to get good detection efficiency and good reliability at the same time. So he says the F1 measure is usually the primary measure. And in this case, they always ignore punctuation and articles like a, an, and the. So then he gives the leaderboard and so on. I guess the first thing they did was Raj Purkar, the guy who built it, made a baseline model, a simple baseline model based on logistic regression. And he got fairly low scores. But then as soon as his data set was released, a lot of other people immediately started working on it, and they started rapidly climbing in their scores. And finally, human performance. I can't get rid of this thing. Let's see. What is this? Yeah, that gets rid of it. Finally, human performance, which is 91.2% in F1 score, was reached in 2016. So that was the end of that. And then they decided, all right, let's, I guess, no, 2000, sorry. That was 2000. Oh, so he says, as of today, as of the day of that lecture, they solved it. But apparently it was back in 2016 that it was actually solved. Yeah, so then they moved on to, so that was easy enough. So they didn't think it would be that easy. So they said, okay, let's make it more realistic. And they said Squad 2.0 will be similar to Squad 1.1, except now you have to be able to tell whether something is an answerable question or not. So we're allowed to ask questions whose answers are not in the passages. And then they have to, there's no leeway on that. If you get a question like that, you have to say that there's no answer. Otherwise, you get a 0 for that one. So, so that's the difference. Basically, saying whether the passage even has an answer to the question. Okay. So here's an example where they ask a question. They give you a passage about Genghis Khan, and when did Genghis Khan kill Great Khan? Well, I guess Genghis Khan is the Great Khan, and so there's no answer to that question. So yeah, so you have to be able to answer questions like that and say that there's no answer. So then here's the Squad 2 leaderboard, I guess the bottom of it. And let's see. So apparently, even in Squad 2, they reached human performance in 2018. And the team was led by the same Stanford graduate student who invented the Squad, or who created the Squad data set. So I guess this is still a big deal. The Squad data set is still considered as something you'd want to be able to do well on if you're interested in question answering. Okay. But then he points out that there's still, you know, if you have a system that can do well on this even human level, it still makes great, it still makes some kind of errors. So here's an example. And so they're asking what dynasty came before the Yuan, and the gold answers are Song Dynasty, Mongol Empire, and Song Dynasty. But the best system, which is based on BERT today, at least at the time of this lecture in 2019, predicted Ming Dynasty, which is wrong. You can any human being can read this and see that the Ming Dynasty was well, it said that the Yuan Dynasty was preceding the Ming Dynasty. So you know that the Ming Dynasty was after the Yuan Dynasty, and so it's wrong. So even BERT didn't get this one. Okay, other limitations, only span-based answers. You can't look at a passage and ask a yes or no question, or ask why something happened. You can only answer, it's just this very restricted form of question answering that you're allowed to do. The passage has, you have to find some subset of words in the passage that directly addresses the question. Other kinds of questions, you're not even trying to answer. No inference, questions. So let's see, questions were constructed looking at the passages. This is not really what people who need information, it's not going to satisfy them because it doesn't contain more general answers to more general questions. But at least it's a start. It's something that you can start to rank your neural question answering systems on. And if your neural question answering system doesn't do well on this test, then it's not going to do well on any more advanced test. So, so apparently it's still useful. Okay, so now they talk about the Stanford Attentive Reader, and there's something really weird about the you know, about the lecture where they gray this part out, and they actually black out the sound during which they're talking about this graduate. Apparently, she was a TA, a former TA. So I don't know what reason they have for doing that, but all they leave, they gray all of this out, and they just leave Dr. QA because I guess that was something, name of her paper or something like that. Anyway, Stanford Attentive Reader. So that's the one that they start talking about in this lecture. And let's see, get this. Flipping to the right page here. So they give sort of a schematic of this. And this thing here is a bidirectional LSTM. So there's one LSTM going backwards and one LSTM going forward. And these are the words of the question. And the words of the question are encoded and fed into these LSTM networks, just as we've seen before. And they do the same thing for the whole passage. They encode the whole passage this way too, by inputting all the words into this bidirectional LSTM. And then I guess the final hidden state comes out and goes into this piece here that decides what, and it selects which passage should give the answer, and then the answer comes out. Let's see, they don't go into a lot more detail than that, except that they're using attention to match the question vector with a passage. So you can imagine that out of this comes a vector that represents the question. Out of this bidirectional LSTM comes a vector. The final hidden state output is a vector that represents the question. And you do the same thing with the passage, and then by comparing those two vectors, you then select the part of the passage that has the answer. And they do it by some attention mechanism. So let's see. So now they go into a little bit more detail. And apparently the way they do it is they just build a model that implicitly looks to match the start and the end word. In other words, you're looking to pick out a span of the passage that answers the question. And one way to do that is to pick out the start word and then pick out the end word. And then all the words from the start word to the end word are the answer to the question. So that's what this Stanford Attentive Reader does. It builds a model that implicitly picks out the start word and the end word. So that's done by these two weight matrices that you try to solve for in the model. So you're learning these two weight matrices, and then the output is that it predicts the start token. And then the output of this one, once you've learned W prime, is it predicts the end token. And then this is, let's see, I'm not sure what, okay, so bidirectional LCMs. I'm not sure what the P is here. I guess P is a passage, but I don't know what the squiggle above it means. So you're comparing the question to all the words in the passage. I think that's what's going on here. And you're calculating some kind of a score, an attention score, that each word in the passage has with the question. And then so there's an attention score that tends to predict the first word, that's this one, and an attention score that tends to predict the last word. So it's basically looking for comparing the question to all the words in the passage and calculating a score for the, I guess, for the likelihood that it's the first, that this word begins to answer the question, and then another score for an attention score for whether this word is the end of the answer to the question. And so that's sort of the idea behind the Stanford Attentive Reader. It learns the weights, these two weight matrices, such that it predicts attention values that give you the right start and end words. So let me stop here for a moment and see if there are questions that we can talk about. Okay. Okay, so then he goes back and looks at these squad 1.1 results. I think he's already mentioned that there's a human level performance was 91.2, but this Stanford questioning answering model, and here's the paper, got almost the best score, not quite the best score. But it was, of all of these models, he mentions that it was the simplest one. They just built a model based on a simple concept and trained it well, and they got almost the best result in the squad 1.1. So then he talks about some improvements that were made to this for a second round. So the Stanford Attentive Reader ++, And let's see. So the first change in the model was this special. It's some kind of an attention, but it's with respect to some kind of what they call a sentinel vector. I'm not sure if they say that anymore. A sentinel vector is just a randomly initialized vector, and that's this Q. And then let's see. Well, I'm not sure. Yeah, Q is some randomly initialized vector, and then they learn the weights for this attention score. Let's see. They don't go into much more detail about that. And the second improvement is that they use a deep 3-layer bidirectional LSTM. So it's just basically this thing multiplied by 3. This is the bidirectional LSTM part, and they just make it deep. It's 3 deep. So that's the second improvement. I guess this part, the first improvement, is that instead of just using the start and end states, instead of looking just at the attention on the start and end words, they build an attention that that looks at all the words. So it does make that improvement. It doesn't just look for start and end words. It looks at all the words and figures out the answer to the question based on an attention an attention score that they calculate for all the words, not just for the start and end word. So that's the first improvement. The second improvement is to make it deeper, and then the third improvement is to concatenate is to add on to the encoding of the word. So you got not only the word embedding, but you also add part of speech and named entity recognition tags. So remember, part of speech means like verb or noun or adjective, whatever. And named entity recognition tells you whether it's a one-hot encoded. It just says, is this a named entity? Is this like the Green Street building or something like that? That's a named entity. So they tack each of these things on, they concatenate it onto the representation of the word. They start with the basic word embedding, then they tack on this thing for part of speech and named entity recognition, and then they tag on a term frequency, which is basically the unigram probability, the probability that this word occurs in all of Wikipedia. So this is basically adding bits of information that turn out to be useful. And then they also add this exact match. So that would be like a one-hot encoded. Does the match appear does this word appear for each word in the passage? They're asking, does that word appear in the question? And then, I guess it's not just one-hot encoding. It's three one-hot encoded features. One is one-hot encoded for whether the exact word appears. The second one is whether the word appears, whether it's lowercase or uppercase. So, for example, the word in the question might have an uppercase first letter, but then in the passage they might find that word but with a lowercase. So, but then in that case this would be 1. This would be 1 because it says that there's a match, but it's not low. It's not a case matched word, but it's at least a matched word. And then the lemma. Remember, the lemma is the stem of the word. So here they would say, well, the word didn't exactly appear like let's see, like the question might have contained the word multiplied. And the answer might have contained the word multiply. Sorry, the passage might have contained the word multiply. So you're looking for multiplied, but at least you got multiply. So the stem is there. So that would mean that this would be one-hot encoded. In that case, it would be 1. You didn't find the word multiplied in the passage, but you did find the stem word multiply in the passage. Is everybody clear on that? I don't think we've talked about this lemma term, except in the we did go over this in the FastAI NLP class, but I don't think they've talked about it too much here. Okay, aligned. And then there's this other feature, which I'm not sure about. It's called an aligned question embedding. So this apparently comes from a whole nother neural network. The alpha is an attention score it's all computed by another neural network. So it's a little bit of a complicated. Alpha is a simple one-layer feed-forward neural network. So this looks like a dot product between the passage and the query word. And it actually looks like a softmax kind of a score. So yeah, but I don't have too much more understanding of that. Okay, so then he just sort of takes a step back and says, okay, what have we done? Well, here's what you had before neural networks. You had, remember the simple logistic regression models, simple non-neural network models were able to get a score of 51 on the, I'm not sure whether this is squad 1.1 or squad 2, but all of a sudden when you bring neural networks into the picture, they make this huge improvement. And then from then on, the improvements are smaller. So you get up to from 50% up to 80%. And then from there, you get maybe another 10% improvement from Google's best effort, gives you 10% better than what Stanford graduate students were able to do. And again, Google did end up beating human level performance. But then he compares, okay, what is the, breaking down the performance on different kinds of questions, they find that the neural network does better in these areas. So the neural network is the green, and the categorical feature classifier, that would be based on a non-neural network model. So the neural network wins big in when the answer to a question is a paraphrase of it, and when the answer to the question is only partially contained in the passage. Okay, so that's basically saying what do we get from neural networks that we didn't have before?
Hey,
okay, yes, sir.
Do you know what the hard error thing is? What that means?
I don't, and it looks like, and that's weird because that one, the neural network doesn't do as well.
Yeah.
Yeah.
And seems like I don't know, is it the ML model or something that does better? Categorical feature classifier seems to be doing better there. And I'm also was wondering about the partial one. The reason for the neural network doing better, is it because it has extra information that's, I mean, if it's not there in the passage, then it must be getting that from somewhere, or is it able to come to some kind of leaps in logic, so to speak, from its perspective, if it doesn't?
What I'm thinking is that, because it's using attention and so on, it's saying, okay, if I look at the words in the question, I find the words in the passage that are related to it, even though the passage doesn't give me a complete answer, at least I've identified which part of the passage is the most related to the question. So that's what I would imagine that the neural network is doing, whereas maybe the classifier isn't able to find the connectedness of those, of the partial answer. So I guess what we're talking about is a case where the passage doesn't provide a complete answer to the question, but it provides some kind of related information. It would be better to have the actual definition of all these things. Multi-sentence, I guess that means when the answer has more than one sentences in it, but they're doing equivalently. And then, as you pointed out, this would be really interesting too, to understand what hard error means.
Yeah, I'm trying to Google that.
I would guess it's in this paper Chen Bolton Manning paper.
Okay.
Yeah, so that's another thing is like if you really want to get into the details of this, you have to look up some of these papers that that they reference. Yeah, so here's the when they spend basically the rest of the lecture on. They really don't spend much attention on. They really don't spend much time on the last on anything in this lecture, the rest of this lecture, except for BIDAF. So that's what we'll talk about next. So here's a high-level schematic of what this is doing. And one of the new things is that they're using character embedding as well as word embedding. So there's a whole layer of character embedding. And he says that they're going to talk about this later on in the Stanford course, so they don't give too much more attention there. And then there's then there's not only a word embedding, but a phrase embedding as well. And then there's an attention flow layer, which he does talk a lot about, so we'll get into that. And then there's a modeling layer, which he doesn't talk too much about. So it's fairly complex. So the attention layer has, it's an attention flow layer, meaning that the attention flows between the question, which they call the query, and the context, which they also call the passage in other places. The passage is the text that you're given to read to find the answer to the question in. So query context, the relationship between the question and the passage, and then the attention in the other direction, starting with the passage and relating it to the question. So there's these two layers, query to context and context to query, that go in here, that go into this attention layer. And then the word embedding is done by glove, so that goes here, and the character embedding is done by something called char CNN, which we don't know about yet, so we'll have to wait to find out about that. So here's the context words. This is the passage, and here's all the words in the passage. Going into this bidirectional, okay, the words are getting word embeddings, this yellow, and then they're getting character embeddings by the purple. So there's these two inputs into the LSTM, and this is meant to be the bidirectional LSTM because it has arrows going in both directions. So it's just a schematically simpler one. Remember, in previous slides, we've seen the bidirectional LSTM be represented by an LSTM going this way, and above it, an LSTM going in the opposite direction. So that's both encoded in this blue. The outputs of those LSTMs then go into this query to context and context to query attention, the bidirectional attention flow. And let's see, and then this U, okay, so that's the context, that's the context, and this is the query. So there's, the outputs from the context are H's, the outputs from the query are U's, and that's, let's see. And so those are the inputs to this bidirectional flow layer. The U, okay, so I guess these green arrows represent context to query. So they take the U, yeah, they take the H's as inputs, and this part, query to context, takes also the H's and the U's. So let's see, the H's and the U's are the inputs. That's what we're seeing here. So this is just sort of a large schematic drawing that is trying to break things down. And the pieces that we're interested in are going to be these two pieces, the context to query and the query to context part of the bidirectional attention flow layer. Okay, so with that, they go into more detail. And the key, or the sort of the central part, is that attention should flow both ways, from the context to the question and from the question to the context. And so now we're talking about this attention flow layer, which was, remember, this piece here. Okay, so the central part of this is this similarity matrix. that has 6 dimensions. The weights have 6 dimensions. And where does that come from? Well, this is the context word. These are the context words. These are the query words. And this is a Hadamard product between context and query words. Remember, the words have a length, their encodings have a length of D. And let's see, and I guess because there's both, let's see, I guess there's, I'm not sure why there's 2. So they're actually counting.
The bidirectional gives you 2D.
Bidirectional gives you 2D. Okay, so there's 2D for this one, 2D for this one. This is 2D for the context, 2D for the query, and 2D for the Hadamard product. Remember, the Hadamard product is a vector that's just the element by element product of these 2 vectors. So it's going to have the same dimensionality as these 2 vectors. And because of the bidirectional flow, you get 2D here. So that's why he says there's six dimensions here. And remember this, but this whole thing is a dot product, because that's this WT, W transpose means we're taking a vector which is normally represented as a column vector, but we're making it into a row vector because we're going to do a dot product with this vector. And this is a column vector. So this is a 6-dimensional weight, okay, vector that's dotted into a 6-dimensional vector that's composed from the query and context words. And what does a dot product give you? It always maps into a real a scalar, right? So so each of these Sij's is a weight, is a similarity score that's a scalar. And then if you take the composite, it makes it into a matrix. In other words, for each context word indexed by I, and for each query word indexed by J, you have a score. Okay, so so you learn those weights and get that score, and then he builds this. Then they built this attention out of the score, and the attention is a softmax. Okay, so what happens here? For each passage word, that's the alpha I, you compute an attention. That's the alpha. So the I indexes the passage words. Again, here it means the row in this similarity matrix that corresponds to this passage word, and then this double dot here is basically all the corresponds to the elements of this row vector that correspond to each of the query words. So we're doing a softmax over those, and a softmax always gives you a vector result. It's going to, and that's why he says that it's in it's in Rm, where M is the number of words in the query. It's the number of, basically the number of columns in this similarity matrix. Right, so first you're building an attention score for each passage position that corresponds to each query word. So it's a probability distribution. This softmax is a probability distribution over all the query words. And it basically tells you how related is each query word to the ith word in the passage. Okay, so that's the component that goes into this thing, and so what do? You take each query word and you so alpha j would be the component of this thing, the component of this vector that corresponds to that query word. Then you take the alpha ij, the piece, the scalar piece of this thing that corresponds to, it's basically the probability relationship of that query word, the jth query word, to the ith context word. So it tells you how related that query word is to that context word. And then this is a sum of all these query words. It's a weighted sum of all the query words. So it's basically mapping, and you get that sum for each passage word. So it basically maps each passage word to sort of an attention weighted average of the question words. So that's what this first piece is. for all I. This symbol, mathematical symbol, means for all I. I, remember, is the context, the passage words. There are n words in the passage. There are m words in the query. Okay, so I know that went pretty quickly, but are there any questions about this thing? Basically, we're mapping each passage word, I, to an attention-weighted average of the question words. So it's basically telling you for each passage word how related it is to the question words. And this is something, back to Anant's question about partial answers. This is what I suspect is giving the neural network the edge over finding the partial answers, because it says, well, I'm not sure that this is the answer to the question, but I'm sure that it's related to the question because they've calculated this attention score for each passage word. So some of the passage words will have very low scores, and you can basically throw them out. Those aren't going to be part of the answer. But if it comes up with high scores for some of the words, then it'll say, okay, these are the words that address the question. And even though it doesn't give a complete answer, it gives a partial answer. So Anant, does that make sense as the answer to your question?
Yeah, thanks.
Okay. All right. Okay, so again, why is it 2H? Why is it dimension 2H? Because the query words, each word, as Srinivas reminded us, has two outputs, one from the forward bidirectional LSTM and one from the backward direction. So that's why it has 2H dimensions. Okay. So now it says, okay, the attention flows both ways from the context to the question. We just looked at that. And then the other direction from the question to the context. So now we'll go to figure out how they address that piece. So backwards here, context to question, we just addressed that piece. And now we're going to address the query to context piece. And remember, so we've seen this. We've seen the context to query, and it comes from this softmax. That's how we did it. Now, how do we do the question to context? So here they're looking for a score. They're computing this score, the maximum over the words, the maximum over the query words of this row in this similarity matrix, right? And so this tells you, what does this tell you? It tells you which question word was most aligned to the passage word I. It's the max over J of this thing. So it gives you the score of the question word that was the most aligned to the passage word I. So that's this M. You compute this M, and it's a vector. Let's see, because max over J. Let's see. Oh, max over J. Oh, it's okay. So for each I, it's a real number for each I, but then taking it as a whole, it's a vector because it has n, and it has n. It has one value for each context word. Okay, then you take the softmax over this vector, and that's called beta. And remember, a softmax is always a vector. It has the same dimensionality as M, so it has n dimensions. Let's see, I have to mute someone. Let's see, sorry.
Joseph, I think
yes.
I missed it. Can you explain
Yeah.
what the similarity matrix is again?
Yeah, let's go back there and look at that. Okay, so similarity matrix is actually learned. Let me see, I gotta mute someone. There we go. Yeah, similarity matrix is learned from, you have to learn these weights, okay? But you're basically finding this this weight vector that dot products into this vector to give you the elements of the similarity matrix. So we really didn't say how this W is learned, okay? So your question is a good one. You have to learn this W vector in your neural network. So if that makes any sense. So remember then, and after you learn that vector, you take the dot product of that vector with the context words, the question words, and the Hadamard product. And then that gives you the, and remember, I is indexes one of the context words and J indexes one of the query words. So that's what SIJ means. It's something that relates context words to query words. That's probably what we should think of it as, the similarity matrix.
So where does this come in the diagram that we had just seen?
Which one are we talking about? Here?
The schematic diagram of BiDAF.
Is that this one that I'm showing?
The diagram, yeah, this one, yeah.
Yeah, okay. So where does that come in? Well, we are computing this context to question attention, this alpha, and that comes in context to question. It comes in right here. So so this piece goes in here, and the softmax that they're talking about here is this thing here.
Mm-hmm.
So for each context word, we've mapped it into for each passage word, or I use the word context or passage, they're the same, they mean the same thing. This thing here, alpha, sort of A sub I, is an attention weighted average over all the query words for that passage word. So it tells you how related that passage word is to all the query words, if that makes any sense.
Gautam, I posted a link on the Slack and chat. So if you look at the images in the link, you'll understand better how the similarity matrix is formed.
Should we look at that? Should we look at that now? Let's see.
Yeah, that would be good.
You want to look at that? Okay. Let's look at, let's see, here we go. An illustrated guide to BiDAF. Oh, that's great. Okay. Are you seeing that now? I just clicked on it.
Yep.
Okay. So let's have a look at this thing. It's a Medium article. Okay, so just to refresh our understanding, context is the text that we're asked to read. We're asking our neural network to read this text and then answer this query. So, Singapore, where is Singapore situated? Southeast Asia would be the answer, right? Overview of the structure. Okay, so this is the, I guess it's too big for my screen. Well, let me see. But if I make it smaller, we won't be able to read it. But anyway, so let's have a look at this. Context. So tokenization, we understand what that is. We're representing the context words in character level and word level tokenization, character embedding and word embedding. Concatenate them both. That's what Srinivasan reminded us. That's why you have 2 times D. D, each of these is length D. The concatenation.
The word embedding and the character embedding are D1 and D2, and D1 and D2 together add to make up 1D, and then the 2D happens more because of the bidirectional LSTM. So
yeah, sorry, that's right, yeah, that's right. So you get this dimension plus this dimension, and then the multiplied by 2 because of the bidirectional LSTM. Talks about a highway network, where I don't understand what that term means.
That's like the residual net. It just forwards it. It's the highway network is the other way of passing on the residual. So it's just something to reinforce what you get. It's talked about. He has a 4-post. This is just a summary diagram, and then he gets into each of the pieces in one of the next posts. But highway network is should be familiar with people who have gone through the imaging to where it's similar to the residual network and just reinforces the feeds forward your input so that your backpropagation is healthier and you don't encounter issues.
Okay. Okay, so then here's the two LSTMs, forward and backward, the bidirectional LSTMs, contextual embedding. So this is, I'm not sure what.
That's the third piece of the embedding that generated. If you go back to what they were discussing in the Stanford discussion, he mentions it, I forget the word used, but it's three pieces of the embedding, the word, the character, and then the context, because you place the what you get from the combination of the character and the word is just independent of the location, and the location sensitivity is obtained by the contextual embedding.
But isn't that something you get from BERT? You don't get that. I mean, I thought the contextual embedding comes from the higher level, from the BERT models that were made later on.
As long as you use an LSTM, it's already, I mean, in BERT model, you get it through transformers, but bottom line is you're getting a representation which is sensitive to the location of the word by passing it through an LSTM, which you do not by a glove or a character embedding, which is independent of a word's location and that's why it's contextual embedding.
So it's just the output of the LSTMs.
Yes, which is what you see passing into the out of 2D times T.
Okay, so if you remember back to the drawing that we showed, which I'm not going to go back to because it'll take, well, let's see, it'll take me too long to get back and forth. But we saw that where the outputs of the LSTMs go into the bidirectional flow thing. And so there's a symmetry here for the question, for the, see, look at this, the context, which is the passage that you're reading from, that's all done in this way, but there's a symmetry, the query is also processed the same way, down to here. And then here's where the similarity matrix gets formed. And remember that we're basically finding weights that connect question words to context words to question words and back and forth. So the Sij gives you some measure of the similarity, some measure of the similarity of the context word to the question word for each pair of context and question words. So that's the Sij that's here. And then we saw that from there it goes to query to context attention and context to query attention. I think we treated context to query attention first, and we got this capital Aij. And then we were just about to do the query to context attention, and we got, I think the output from that is something called Bj, and then they get somehow combined this context to query and query to context. That's that attention flow layer that we saw in the drawing, and then these get merged together with the output of the passage, I guess the context embedding, the context embedding. Sorry, I shouldn't mix those words, context and passage. We should always use passage because, well, they don't. But there's a confusion between contextual embedding and context, and they mean different things. The context refers to the passage of text that we're reading from to answer the question, but this means something else. Okay, yeah, so this is the attention flow layer, this piece here, and then there is another complicated part, the modeling layer, which he doesn't really talk about at all, and then an output layer. Well, he talks about it very quickly, he doesn't really tell us much about it, and then there's the output layer. So for this lecture, we're probably, I mean, he spends most of the attention on this part here, the query to context attention and the context to query attention. And we've already gone over the context to query attention, how that's calculated using a softmax. And then the next piece is this one, the query to context attention. Yeah, so did you Did you want to say more about this, Srinivas?
No, there's you know, there's just the first part, and there's the second and the third and the fourth, and so he goes through each piece. So you know, it's fairly complex.
Yeah.
You can just go through. I mean, we don't need to go through it here, but people who are interested can go through each piece, and it's fairly well explained as to how to get through each of the pieces, and then finally put the pieces together through a bidirectional LSTM, which is what the modeling piece is.
Yeah. So I'm going to just briefly go to part 2, where he says he explains in detail all the pieces. So that's something to look forward to. So here's where he puts everything together. Tokenization, we kind of understand that. So this is the passage from reading from the passage that has the answer to the question in it. This is the question itself. Word level embeddings, we've already talked about glove. Word embedding, so now we're here. So I think we understand this part. Then he does character level embedding. That's done with CNN, with a one-dimensional CNN. We're going to talk about that next week. And we end up with character embeddings, and then we put those together. He talks in more detail. This will be great for a reference for next week, I think, because we're going to talk about this one-dimensional CNN thing for context embeddings. Okay, so let's see, convolutional filter. This is more details of the convolutions. I think we'll skip over that because we'll probably cover it next week. Highway network. So this is the piece that hasn't been covered in the class. Okay, so up to here, passage and question, word embedding, character embedding, concatenates together, goes into this highway network, which I'm still not sure what that does. But I guess he explains it a bit here. Well, this will be good to go over. We don't have time to go over it here, but this is a really great reference. And then, so he didn't really explain all the pieces. He didn't explain the.
No, the third piece goes into just the attention, and then the fourth into.
Oh, there's a third part?
Yes, if you just go up, you'll see.
Ah, the next article. Okay, so this is really great. It looks like it gives a pretty much in-depth explanation, and I think that rather than read all the papers that he referenced in this lecture, I think this would be great if we could just go over these 3 articles to try to understand this BiDAF. I think if we did that, we would be in good shape for this lecture. I think that would be sort of the goal, to understand this lecture by means of these 3 articles. Yeah.
Yeah, the next one is the whole attention of how the similarity matrix is calculated, as well as how context to query and query to context attention is calculated, which is kind of the heart of the BiDAF, because that's what is the bidirectional attention flow.
Right.
Here you're just going over attention, so you can skip this since we went over it.
Yeah. So this is the context to query part, I guess.
This is just the general concept. Actually, if you go down, it shows how each of the 2 are, and this is the formation of similarity matrix that Gautam was asking about, and then he kind of takes an example and shows you how. So it's
so this is what the similarity matrix would look like in this simple case. Here's the sentence. In this case, the context, the passage is just one sentence, and the question is another sentence. And so the similarity matrix has a row for each element in the passage, and the elements in that row correspond to the elements in the question. And so it's basically telling you how related is that piece of the is that word in the question to that word in the answer. So where and Singapore have a high value because well, the network has to learn that. The network will learn that that weight should be high. And then on the other hand, it will learn that situated situated has sort of an intermediate score with respect to Singapore. And Singapore has a very high score. So that sort of tells you that that's kind of going to be the answer. Anyway, but this is magic because it's the network that the network learns these weights. How do we get, because the question that Gautam asked was how do the network get, how do we get these? And it comes from the network.
Yeah, if you just go down, it gives a picture of how it gets built up. Just that diagram. If you go a little further down. So the picture. Yeah, there. That tells you how the similarity matrix get built.
So we have a context and a query. We have the embedding of the. So we have that, and we have that, and they're concatenated. Then the Hadamard product is these two, basically the element by element product of these guys, and that's that. So that's the concatenated vector, and this is the weight vector. So this is the weight vector. We don't know these weights, but we know that their dot product is supposed to be the Sij, and we want to. We know the answer to the question, so we train our network to give us the weights that give us the answer to the question. I guess that's the simple way to say it, right? We know the answer to the question, and so we train a network based on the answer to the question to give us these weight elements. And so then the dot product of the weights and the concatenated vector, that is this vector, the dot product of the weights and the concatenated vector is it gives us that element of the similarity matrix from okay, so then we talked about context of query already. And I guess we'll see the attention vector. So the output of this was, well, they called it the AI vector, which for each passage word, you get some kind of a you map that to some kind of an attention weighted average of the question words. And so that's what we should be seeing here. Attended query vector for teeth context word. Perform this for all t to get this matrix. Okay, right. So we're looking at this vector. That page that we were on, which I could go back to really quickly. Let's see. I think. Okay, so keep this. So let's look at this vector. This is what is This is what is the AI vector on. Oops, I've lost my position. Let's see. Oh, this is the wrong. Sorry, I want the PDF document. That's it right there. Can you see what I'm looking at now on this page? This is page 38 of the notes. Am I showing that? Yes, no?
Yep.
Okay, so this is AI. Remember what I was telling you, that this is this maps the passage word I to an attention weighted average over all the question words. The QJ, these are the question words. This is the attention weights that we get from the softmax. So this is AI, and then now I got to find my way back to the, yeah, there it is. This is the AI, okay? And you do that for all the context words, and you get this whole matrix of vectors, one for each context word. So that's the end product of the context to query piece that they then will combine later. Remember, this is all part of the attention flow, the bidirectional attention flow layer. So this is the one direction flow from context to query. And then the next one is, which we haven't covered yet, we haven't talked about yet, is the query to context. Oh, and then, sorry, and then this thing here, this arranging all of these column vectors for all of the context words, you have this matrix, the attended, he calls it the attended query matrix, and he showed that at the beginning here. This is the attended query matrix, I believe. And then I guess he's going to build a similar matrix for the other direction. Or maybe not, maybe he's talking about the similarity matrix.
That is what makes the paper the bidirectional attention flow. So there is a flow of attention. So far we have looked at it in one direction, which is from in the original attention from the query to the values in one direction, right? From question, from, for example, the decoder to the encoder. But in this case, it goes in both directions, from the query to context, from the context to query.
Right, and so we just covered context to query, and that's what we ended up with this matrix here. And now the second part, the query to context. So he says it also starts with the similarity matrix. The goal is to find which context word is the most similar to either one of the query words. I'm not sure what.
Language, you have to go through it in detail, but the language is, I wish he had just made it exactly parallel, but if you look at the back at the similarity matrix, you can think of it, if I'm not mistaken, since I'm talking from memory, but one is taking across, the similarity matrix is dimensions are T by J, where T is the rows, and that's the number of entries in the context word, and J is the number of entries in the query word, and the first attention does the softmax across the rows, and the second does, if I recall correctly, again, the softmax across the columns.
So
of the similarity matrix, and that's how you get both, but then you go through a little bit more of a complex.
Yeah, it's not exactly symmetric. It's not exactly symmetric, right? So the page following, I guess this is what we're going to actually cover now. So this is the context to query part, and we ended up with this column vector AI for each one of the words, in the context, in the passage, right? Now we're going to calculate BI, which is for each, so it's going to be another vector that encodes the relationship of in the other direction from query to context. So, but it's not done it's not done symmetrically, okay? So, so here he tells you how he actually does it. So he's looking at that similarity matrix, sorry, and the row of the similarity matrix, I'm sorry, he's looking at the maximum over the columns in the similarity matrix corresponding to a given row. So the row corresponds corresponds to I, the passage word, the word from the passage, right? So for each word from the passage, we're looking at all of the elements in that row in the similarity matrix. Remember, J indexes the query words. And so we're looking for the maximum, the one that has the maximum value. And that's going to be a number in the real, it's a real number, it's a scalar. But we're going to get one of those for each context word. So that's why we get a vector out of it. Does that make sense? For each context word, we're going to get a scalar when we do this. And going back to the, so think of this MI as a vector that we get from the similarity matrix. And let me go back to that. So here's the similarity matrix. And here's a context word, let's call it, let's say small. We're going to look at the fourth word in the passage, small. And then we're going to look at the similarity matrix, the S, so S41, S42, S43, S44, and we want the maximum. So that's going to be this one, right? We're going to get, so M sub 4 is going to be this element here of the similarity matrix, okay? Then the next word, country, we're going to look for, again, we're going to look for a maximum over this row. The row, in other words, the row of the similarity matrix elements corresponding to all the question words. And again, the first element is the maximum value, right? If you look at the color scheme, purple is -1, kind of this shade corresponds to somewhere here, but this orange shade corresponds to somewhere here. This is the maximum value. So, so M5 is going to be this element, and so on. You can do the same thing. M6 is going to be this element. It looks to me like this is the maximum. Located, situated. These two words are the most similar. So does that make sense how we're getting the M sub I vector? We're going over this similarity matrix and picking out the maximum of each row. The element corresponding to the maximum of each row. So in that way, you can create the MI vector. And then, okay, yeah, and you do that for each of the context words, and then you end up with, the MI vector. So if that makes sense, does that make sense? Okay, that's where we are here, the M sub i's. Next, we take that vector M, and we construct a softmax over it. And since the vector has M elements, the softmax has M elements. And remember what the softmax is basically converting each element to a probability between 0 and 1, converting each element. So it's giving us this thing called beta, which is a vector, which has the same number of entries as the context, the passage does, words in the passage. Okay, so now it's creating this thing that's similar to the AI. It's kind of some kind of an attention-weighted average of the context words, where this is the attention, and these are the context words. So we're weighting each context word by this attention, and then adding them all together, and that gives us this C prime. Okay, so C prime is somewhat similar to the AI that we created, or yeah, and then but that's only a piece of this thing. So the BI is going to be this vector that has in it the context word, the AI that we calculated in the previous page, the Hadamard product between the context word and the AI, and then the Hadamard product between the context word and this thing C prime. So this is where the symmetry is. Otherwise, the details are a little different, computing the AI and the BI. We have, in this vector BI, we have CI times AI, the Hadamard product of the context word, of the ith context word with the ith element of that A vector that we calculated on this previous page, the attention-weighted question word, corresponding to that context word, that's that. And now we've got the attention-weighted context word, and now we form the Hadamard product between that C prime and the context word embedding itself. And so that gives us this 8-dimensional beast right here, 2 for the context word, sorry, 8H dimensional. 2H for the context word. Remember, one comes from the forward and one comes from the backward LSTM. AI has the same dimensionality. CI has the same dimensionality. That's 2, 2, and 2. Sorry, CI Hadamard product with AI. Since CI and AI have the same dimension, the Hadamard product has the same dimension. So that's 2H, 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 and then again another 2H, so that makes 8H. So that's the view of it from the Stanford lecture, but Srinivas fortunately found us this nice document that gives us another look at it. Let's see. So query to context. So how does that map into the Z? Yeah, I think this is basically what we did. The Z vector that he talks about here is the same as our M vector. And it's going to be the maximum here, the maximum here, the maximum in this row, the maximum in this row, this, and so on. It's basically making a vector out of the maximums of each row, right? That's what we're getting here. Now I'm a little confused because this is Asia, and the maximum in this row is not, oh, it's 1. It says 1. So the color scheme has changed here, I think. That's what we have to be aware of. Now the color scheme goes, color scheme goes from 1 to 8, whereas here the color scheme goes from -1 to 4. So if you look at the maximum in this row, it's this color here, which is somewhere around 1, right? This word where is the maximum, and it corresponds to somewhere around 1. But here we see that it's purple, sorry, dark blue, but that's okay because the color scheme is different, and here dark blue still corresponds to 1. Does that make sense? So this Z is the same as our M that we looked at in the previous, in the Stanford lecture slide. Okay, so now what is he going to do with it? Similarity matrix, maximum of each row, this is the Z. Attention distribution,
Joseph,
yes.
Does he take just one, just one word, which is the maximum?
Yes.
I feel like he takes like top N max and then does a weighted.
Yeah, that comes later, right? That comes later. So let me go back to that page. So this is a good question. So here, I'm sorry, I lost my. Uh-oh, that's gonna hurt. Now I have to get back my. Too many things open. There it is. That's what I want. And then what I want is the PDF document that you're asking about. So this is the Z. This is the Z that we just went through, right? But as you said, he then makes a linear combination. He makes the softmax, and then the weights come out of that softmax, and then he makes a linear combination of the context words based on those weights. That's what you're asking, right?
Okay. So
but the M itself, so the Z itself is just the vector constructed from the maximum element in each row, and that's what we call the M vector in the Stanford lecture. And then you're right. More processing happens. We calculate a weighted average of the. We end up calculating a weighted average of the context words.
So M is the. So M is a set of maxes across each word in the question. Across all the question words.
That's right. M1 is the maximum of the similarity matrix row 1. M2 is the maximum of the similarity matrix row 2, and so on. And that's the same as his Z, right? And so if we look, we can see, okay, the maximum of row 1 is going to be 4, right? It's this. Now I'm confused because that says 8 here. I mean, he said that there's a similarity matrix. Row 1 has the maximum here, which corresponds to 4, a value of 4. But in here, it's mapped to 8, and I don't understand that. maximum of row 2 would be one of these two words, is or situated. I can't tell which one. Probably is more orange. So where does that correspond to? Somewhere around here, somewhere around 2, right? If we go down here, we should see a value of 2, but it's not. It's more like 6. So I don't understand some of this. I mean, I was able to explain why this one is 1, why this one is dark blue, because that corresponds to 1. And if you look at the last row, the maximum is here, which corresponds to somewhere around 1, right? So the maximum of row 9 is 1, and that matches here. But I don't understand this mapping here. But anyway, I'm pretty sure that it's what we said, is that the z vector in this Medium article is the same as our m vector in the Stanford lecture, which is just and each element corresponds to the maximum across the rows. And then further processing happens. So this is the maximum across each row, just as he said. This is a similarity matrix. Maximum of each row, that gives this vector. And that's the z, okay? Then we do the softmax to convert these values into probabilities. And that gives us an attention distribution. And then, let's see. Now, what's going on here? H is a weighted sum of the most important words in the context. All right, so I understand up to here. I don't understand what's going on here. We duplicate this vector. T times T is the number of context words in the Medium article. Weighted sum of the most important words in the context. So this might be our, I don't understand.
You have to multiply the scalars by the individual vectors in sum to compute the actual attention distribution. So that's what he does up above, where he shows each of those scalar values multiplies the vectors, each of the vectors, and then you sum them to get your single column.
Oh, okay, that's right. Okay, right. So this is flowing. I mean, the logic is flowing down this way. I'm getting confused by the arrows. So I thought this was something that came in from below, but no, this is something. So this attention vector that we just calculated. Remember, we took the z or the m, whatever you want to call it, and then we scaled it by basically normalized it to get a softmax. Which means all the entries are between 0 and 1. And now he's taking apart, as Srinivas said, each entry gets taken apart. So this is the max, this is the first element, this is the second element, and so on. And then we multiply this vector h, which is the context vector. So this is the CIs, I guess, the context. The embeddings of each of the context words, because it's the dimensionality is t. So each context word gets multiplied by the corresponding attention and then gets added together. That's what this green vector is. So this is what we call the BI, I believe. And let me go back to that Stanford lecture. Yeah. So here's the attentions that we calculated, and now we multiply each context vector by its corresponding attention, which is the softmax probability. Add those all together, and then we get this vector, which he calls, in this Stanford lecture, he calls it C prime. Now back to the Medium article, this is C prime, okay? So each attention value gets, each context word vector, the embedding of the context word gets multiplied by its corresponding attention, corresponding probability from here. And then you add them all up to get this thing called C prime. And then, let's see, why are there, oh, and of course, let's see, duplicate, okay, and this gets duplicated T times for the next operation, which I don't know why they're doing that. Duplicate T times, what happens next? Merge, mega merge. Okay, I don't understand what happens in this.
I think the duplication is just to get the matrix dimensions and,
2D times T, right.
Sometimes they say you do things for convenience, and I think this is more a convenience thing, so that it just duplicates it in order to get it to the same T dimension, and then that makes it easier for them to merge to get the 8D vectors that they get next.
Yeah, and I guess in practice you wouldn't have to do this because broadcasting would do it for you.
Yeah,
when you use tensors and so on. So mega merge, the original context matrix,
and the two matrices that you have just generated are the U tilde and the H whatever.
Okay, so this is the query to context, which is the one we just looked at. So that would be this. That would be.
That's the previous one, I believe, or it could be the later one. One of these second two are the ones that we just generated, and H is the original, and then you get the 8D by the equation that's just below.
Okay, right. So we had a context to query part and a query to context part, and that would be these two. Right. And then the original context matrix,
which, if you recall, combines three embeddings: the character, the word, and the context. So it's so what
character, word, and context, right?
Right. That's in H, and then the two attention, the bidirectional attentions are in U tilde and H tilde, and then they throw all of that bucket together and do the next 8D multiplication learning.
Okay, so they all have, so that points out that these three matrices all have the same dimension, 2D by T, and we see that here, 2D by T. And so this is called the H tilde matrix, which is the context matrix that captures information about the important words in the context with respect to the query. Okay, now let's just back up and look at the U tilde just to make sure we understand. So we understand the H tilde, we've seen how that was generated. Let's go back and see. Okay, and here's the, and here's the U. Okay, so this is basically all the Z's lined up next to each other. That's the U tilde, and it's also 2D by T. Okay, and then the H original was just the context words themselves. Okay, so then the step 9 is the mega merge. Unfortunately, it's not as simple as stacking these three matrices vertically. We make use of another custom function called beta. And again, this beta is not the same as the beta that we looked at in the Stanford lecture. So let's see. Okay, but it is the BI that we looked at in the Stanford lecture. So I guess this is the mega merge. It's right here. The BI, right? But he says this is 8H, and we were. It looks to me like this is what the same thing as the mega merge.
It is. It's just the notation you have to keep translating, and it just he just sticks with 2D for each. So it's 8D here. He uses H and switches it around.
Yeah, H and D are interchanged.
Yeah, the same. So it,
yeah. Okay.
Because actually the Medium post talks about the paper, not about, and Stanford begins to use its own notations, which are different from what is in the paper. So.
I see. So the Medium post to me seems to be like the better choice, but we do see the correspondence between this and the BI calculated in the Stanford notes, right? We have the original vectors, the Hadamard product of the this is the context word, and the query to context object that we calculated, and this is the context to, sorry, this is context to query object, and this is a query to context object, and this is a Hadamard product. Okay, so now we have this mega merge matrix by G, B, H, U, where G is the ith column after the corresponds.
He's just explaining, it's better explained in the picture, Joseph. If you just go down, you can just see that it's just the same thing as in the equation, the two pieces and then the two cross products. That's it. That's all he's trying to portray.
Okay, so we have context matrix, U tilde matrix, H tilde matrix, both of which we calculated. Remember, this is the stack of the Z vectors, and this is just a repetition of that one vector that we calculated. Then, let's see, okay, so then he puts them together like this, and what's going on here? This is one.
He's just illustrating the Hadamard product of.
Oh, yeah, okay. So Hadamard product, Hadamard product.
And the third one is the Hadamard of the first two, and the fourth one is the Hadamard of the first, and then the third, which comes in through this arrow. So it's just that explanation pictorially of the equation that you have.
Yep. So this is a pictorial, as you say, this is a pictorial representation of the equation in the Stanford lecture, the BI equation. All right, so then that's equal. So, okay, so we get here. We kind of understand how we got here. Then what do we do? G, he makes, okay, so this is the G, I guess. Perform this for all T to get a query-aware vector representation of all context words. Okay, so this is one vector that corresponds to one context word. And I guess you want to construct this for each context word and then stack them side by side. Yeah, and then that's this final output, I guess. The giant matrix G contains all information in H, U tilde, and H hat. That is, each column vector in G is a vector representation of a context word that is aware of the existence of the query and has incorporated relevant information about it. So that's that.
And then you can go to the next article, which finalizes how you feed that into the model and get the output that you finally desire.
Okay, so there isn't okay, so there's a total of four articles then, right?
Yes.
Okay.
The first one is just an overview though.
Yeah. Okay. An illustrated guide with minions. Oh, this is going to be great. Oh, let's see. So here's our G that we just calculated for each context word. It's a query-aware vector. That's what we got here. So we got this special big matrix G. Think of the words in the context as an ordered bunch of minions. All right. The words in the context. All right. Each of our minions has a brain in which he can store some information. Right now, the minions' brains are pretty cramped. The current brain context of each minion is equivalent to the 8D by 1 column vector of the context word that the minion represents. Okay, so this is that query-aware vector of the query-aware vector representation of the context word. Okay. Now the length of this thing, 8D by 1, okay. All right, so there's that minion. The minions moved on and attended the contextual embedding lesson, conversational lesson during which the minions had to talk to one another through a messenger app called ByLS. That's what we just came up with, right? So the ByLS allowed the minions to learn each other's identity, which they learned in the previous 2 lessons, blah, blah, blah.
In the first part of this, he basically just takes you through an analogy using minion saying, you know, how do you create the 8D by 1 by using the ByLSTM to generate contextual, blah, 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 and then eventually end up with the 8D by 1, which includes all of the various ways by which you have incorporated attention from query to context, context to query, and individual word, character, and contextual embeddings. That's all these words.
Okay, so
mean. So you can skip all that to get to the what you do with the 80 by 1, which is further below, or 1 by 80.
So, but this is interesting here. He's saying what's in that vector. It's basically the word knows its position in respect to the whole passage. It's aware of its neighbors, and it knows its importance. It knows how related it is to the query. So that's kind of an interesting way to think about this vector. Give it that kind of information. Now this is the part we haven't covered yet, the modeling layer. Modeling layer is 2 layers of by LSTM. The input to the modeling layer is G, that's the vector we just talked about. The first by LSTM converts G into a 2D by T matrix called M1. M1 then acts as an input to the second by LSTM layer, which converts it to another 2D by T matrix called M2. So here's schematically, let's see, these are the G vector, the G matrix goes into the modeling layer matrix containing information of all context and query. Okay, so this is the 2-dimensional, well, he doesn't show 2 dimensions. There's a forward LSTM and a backward LSTM, but apparently there's 2 of these.
No, the second one is the one below. So each of them gives you a D by T, which it concatenates to get 2D by T.
Okay.
And then feeds it into M2, which is this second diagram. Sorry, which feeds it into the second LSTM, which yields M2. The first one yields M1.
Okay, so that's what he meant by this 2 layers of by LSTM. Okay, the first one produces M1, and the second one produces, wait a minute, the first LSTM produces M1, yeah, just as you said, and the second one produces M2. Okay, so G goes in, M1 comes out,
M1
and then
goes in, M2 comes out.
Right, okay. This is M1 going in, M2 coming out. M1 and M2 are yet another matrix representation of context words. The difference between them and the previous representation, which they mean G, I guess, is that M1 and M2 have embedded information in them about the entire context paragraph as well as the query. Somehow I thought G had that in it. I mean, I thought that G had information about the query as well as the context word, but and maybe I missed something. Okay, minions speak. This means that our minions now have all the information they need to make the decision about who should be in the answer gang. Lastly, I also know my neighbor's importance to Mr. Query. Okay, so that's the things we saw last time, and now the fourth piece is each word now knows its relationship to, it's not only its relationship to the query, but the relationship of all its neighbors to the query. The Singapore guy now has all he needs to decide if he should join the answer gang. So that's the output layer, I guess. For each word in the context, we have 2 numerical vectors that include the word, that encode the words relevant to the query. That's, I guess, the M1 and the M2. So then he combines them with G to get 10D by T. So, so the M1 has 2D by T and the G has 8D by T. So I guess that's where he gets the 10. So M1 and M2 are vertically concatenated with G to get these 10D by T vectors. We then obtain P1, the probability distribution of the start index over the entire context. And then I guess we want P2, the probability distribution of the end index by the same way. So let's see, And then, okay, and then he illustrates that. But I'm just going to scroll through quickly to see where he's getting to. Once you have P1 and P2, the best answer span is simply a substring of the context with the highest span score. The product of the P1 score of the first word in the span and the P2 score. Okay, that makes sense. So, okay, so the product of P1 and P2, the probability of the start word and the end word for each span is calculated, and then they extract the span with the highest product. P1 and P2, each word in the context associated with one P1 and P2. So these are the P1 values. Again, this is the probability that it's the first word in the answer. And the P2 values indicate the probability of the words being the last word of the answer. So you have that. Then I guess you multiply them together and find the one that's the maximum. Let's see, but wait, how does that? Oh, I see how they construct the answer by Southeast Asia. Southeast being the maximum probability for the first, to be the first word is Southeast, and the maximum probability to be the last word is Asia. So if Southeast Asia, okay. Okay, so then I guess it's showing how the span scores are computed. Singapore is A.
Yeah, the only exception, Joseph, is the fact that if you're, and I may get the wording incorrect, but if your P2 is earlier than, or your end word is earlier than your start, then you have a problem. And
yes.
So there is a way to deal with it that he talks about in the end, and that's it. That's the exception. If, however, that's not the case, you already have the answer.
Okay. But I thought he switched from computing P1 times P2 to just looking for the maximum of P1 and the maximum of P2.
No,
that's where I got a little
it is
confused.
P1 times P2, the max of the products, because P1 is the start probability, or the probability of a word being the start of your answer, and P2 is the probability of that word being the end of your answer. So you do the
Okay.
P1, P2 multiplication, whatever yields the highest, provided your P1 word or the word you've chosen for P1 is ahead of the word that you've chosen for P2. If that's not the case, then you have to deal with that exception because it's switched. Your end can't be ahead of the start, right? So then you have to deal with that situation.
Okay, so you're looking for the two words that have the highest product in these two, the two words, one selected from this matrix and one selected from this matrix that have the highest product. And so obviously in this case it would be Southeast times Asia, but as Srinivas said, in other cases, okay, and that makes, in this case, the first word, the start word comes before the end word, so everything's logically consistent. But there might be cases where you go through this exercise and you find that the first word is, that the one that's selected as the most probable first word is actually after the one that's selected as the most probable last word. Then you have a problem, and Srinivas says that there is a method for dealing with that exception. I'm not sure how they would do that. I would just give up. I would just throw up my hands and give up. But maybe they back off to the next most probable start word or something like that. I'm not sure how they actually do that.
He just covers it in the last paragraph. I think he computes all just the one below that. If you could scroll down a little bit, he just has a paragraph.
Oh yeah, there we go.
Right
okay,
there.
and that particularly says, there we go. Context word, the highest P1 comes after the context word with the highest P2. We have a bit of work to do. In this case, we need to generate all possible answer spans, then calculate the span score for each of them. All possible answer spans, that's a large number, especially if you have, so it's all combinations of two words out of the passage.
It's actually whatever number is between this. It's not just 2, right? Because it could be, it's a span. So it could be of any length.
Yeah, but the span is given by the start word and the end word.
Yes, but he's talking about, I think, multiplying, if I'm not mistaken, all possible answer spans and then the span score for every one of them.
Yeah, so, but the span score you're right. Is just the product of the start and the end word score. So it's basically combinations. It's basically the number of combinations of context words taken 2 at a time, which can be very large. If your context, if your passage is a paragraph of 100 words, then that can be a very large number that you have to go through. Yeah, so that makes sense. And then you just pick the one with the
highest score.
Oh, I guess you don't take all combinations of 2 words. Oh yeah, you do, because the ordering matters. So a combination of word 2 with word 10 is, yeah, combinations are what you want, not permutations. Yeah. But then you have to filter these, right? I mean, you have to filter these combinations. The start word has to come before the end word. So
combination would do that automatically, right?
Yeah, like that's right. That's right. That's right. Yeah. So if there were 5 words in your context, then it would be 5 factorial over 3 factorial times 2 factorial, which is 5 times 2. You'd have to go through 10 possibilities. Yeah. So that's not terrible if the passage length is 5 words, but if it's 10 words, then it gets well, then what would it be? It would be 9 times 10 divided by 2, or 45. Well, that's not too bad if it's 10 words. Yeah, okay, so it's not terrible. Even if it was 20 words, it wouldn't be too terrible. So yeah, it would be like 19 times 20 divided by 2, 190. So even for 20 words, it's reasonable. You have a reasonable number of things to check, of span scores to check. So that makes sense. Okay. Anyway, so thanks to Srinivas, we actually got through. I got a really good flavor for what this is, for how this works, and I really like these 4 papers, these 4 little Medium articles. This guy's a really good writer, and it'd be good for us to read them all, and just make sure that we got all of the juice out of this Stanford lecture. So so there we have it. We're at the end, and next time we'll continue with number 11. Which I guess it computes these there's one-dimensional CNNs, and see how that. I'm always curious to see how that factors in, how CNN factors into NLP, because they didn't cover that in the FastAI class. She just Rachel mentioned it, but she didn't cover it. So I'm excited to see lecture 11. Are there any questions that anybody wants to raise, or points that anybody wants to raise? Announcements that anybody wants to make? All right, then we'll see you in a little while for Kaggle. I went